Hi y'all, so today I'm just going to go through, on this video, I'm just going to go through our recitation video. Oh, the light. I'm not in my normal setup area because I'm waiting on a delivery, so I'm in the living room. So sorry if I have to pause randomly in the middle of the video. It's one of those deliveries that you actually have to be there when it arrives. Okay, so in your own words, describe the following terms. Isomers, constitutional isomers, conformers, stereoisomers, enantiomers, diastereomers, mesocompounds, chirality, plane of symmetry, optical activity. Okay, so first I like, to start with isomers, and then I break isomers up into constitutional and stereo. Sorry, these kind of ran into each other. And then I break stereoisomers down into enantiomers and diastereomers. So this is kind of my basic tree. So isomers, constitutional isomers, and isomers are anything that has the same, I don't even remember what this formula is called, but this like very basic formula with the carbons and the hydrogens. And then constitutional isomers have different arrangements of that. So would be an example of that, where these have the same number of carbons. Well, they might have slightly different number of carbons, but you know what I mean? When there's like this versus this, there's 5 carbons in both and 12 hydrogens in both, but they're arranged differently. That's constitutional. And then stereoisomers is when they're arranged differently in space. And to be more specific, they're enantiomers, which are right and left-handed. Non-superimposable mirror images. And then diastereomers are everything else, is what I like to say. And conformers, though, are different. So I like to put attention on this just because I want you to see that you can rotate on a conformation or even on a Fisher projection. You can rotate these 3 things here and not change to a different isomer. But if you're breaking 2 bonds and switching them, so say that's A and B, and you switch it to B and A, that can make a different isomer. So conformation and rotating around a single bond is different than having stereoisomers. So I do like to point that out. So then we've covered conformers, enantiomers, diastereomers, mesocompounds. They're kind of their own thing. They are not really an enantiomer or a diastereomer. So I will probably be like, let's see, I would probably put meso down here because they sort of have 2 chiral centers, but they're identical to each other. So that's when there's the plane of symmetry, A, B, C, and then the mirror image of that, because that plane of symmetry means that these 2 are identical. So they're not isomers at all. You take kind of this enantiomers and you mix it in with a diastereomer and you come up with a not isomer. They're identical. They're not isomers. So they kind of go in their own category. So however you want to represent that is fine. And then a chirality or a chiral molecule, that's what you call one of an enantiomeric pair. That's a molecule that has no plane of symmetry, no symmetry plane, and it does also have optical activity. So all these words are related, but they're not exactly the same. So that's probably how I would make my flow chart. But however you did it is probably fine, as long as you're defining terms properly and you understand the relationship between them. Okay, so first what I want to do here is say that it's easier for me to visualize stereochemistry when it's in the hexagon shape. So I'm seeing here that this is pointed up and this is pointed down. So this will probably be, I'm going to decide that it's a wedge. It could be either. And this is pointed down, so this is going to be a dash. And just to make sure that that's true, I'm actually going to do my little system where I would go, this one's equatorial, axial, equatorial, equatorial, axial, equatorial. So if this carbon 1 is equatorial, carbon 3 also must be equatorial. So because it's axial, it must be OH. So one's a wedge and one's a dash. I think based on the way that we're looking at it, normally when you convert from chair to a ring conformation, I feel like you can choose either wedge or dash, and it doesn't matter as long as it's cis or trans. But because it's drawn pointed this way and this one's pointing up, I'm going to keep that consistent. So up will be a wedge coming towards me, and down will be a dash going away from me, and I'm going to keep it on this side of the molecule. And if you do look at it like that, you can see there appears to be a mirror image relationship between these. So that was my first order of business, is to convert this to a way that it's easier for me to see. Now, is there a plane of symmetry in the middle of this? No, because if you reflect this across here, it would need to be a wedge, and instead it's a dash. So no plane of symmetry, and this carbon right here has an oxygen, CH2, CH2, and then a hydrogen. So then let's go to the next carbon, CH2, CH2 here. So this is another carbon with H on it. This carbon has a carbon and 2 hydrogens attached to it. This carbon has a hydrogen and an oxygen attached to it. So this wins. So these are different, and this is a different priority. So I would just say 1, 2, 3. And this is going left, and the hydrogen is already pointing away from me, so it's S. Let's see. We actually can do the same thing. We can use the same assignment of priority. 1, 2, 3. And this is going right. So this, but the hydrogen's pointing towards me. There's a hydrogen here on this wedge, right? So that would be R, but the hydrogen's pointing towards me, so I'm actually going to say it's actually S. So we have S and S. So now let's look at this one over here and see what the R and S configuration is. 1, 2, 3. I'm using the same priority I assigned over here. That's R. And then, let's see, 1, 2, 3. 1, 2, 3. That should be S, but it's pointing towards me, so it's R. Did I do this one right? 1, 2, 3. Yeah. So this is SS and RR. So in my opinion, these are enantiomers. So this challenges you to know your chapter 4 stuff really well, plus it challenges you to know your visualizing molecules really well. So I did go ahead and assign the RNS configuration to this just to make 100% sure. I'm going to get a clean piece of paper so you can see. But if it's easy for you to visualize, and you can just use this, and you can look at that and you can know, no problem. These are mirror images. If I flipped this over, let's see, the molecule is kind of like one's pointing up and one's pointing down. If I flip it over, that'll be the opposite. If you can visualize that and see that they're mirror images, like if I flipped this whole thing over, this thing that's pointing out towards me, when I flip it over, will become a dash. And this thing that's coming away from me, when I flip it over, will start coming towards me. So if you can do that and see, like, oh, see, that's clearly the mirror image. More power to you. I'm not great at visualizing that. And actually, on these cyclic ones, I always had a modeling kit ready so that I could practice a wedge and a dash and get used to that. Okay. So, so in that one we had 2 chiral centers, and they were not meso compound because they did not have the plane of symmetry right there in the middle. And so we know that there are enantiomers and not meso. Okay, so, and I just got interrupted. I think I finished up by saying these are enantiomers, but I do want to say there were 2 chiral centers here, and here. Now, there's been some confusion about stereocenters. So I'm going to clarify. There are stereoisomers, and a subset of stereoisomers is enantiomers, right? And then everything else is diastereomers. And similarly, stereocenters have a subset called chiral centers. Stereo or stereogenic. And diastereomers don't really come into it because it's either going to be a chiral center or it'll be kind of like a cis-trans is all you need to worry about for this class. And you don't really need to worry about this for this class. It's come up a few times, so I just kind of want to address. A stereocenter is broadly referred to as swap two groups. Actually, I want clean paper for this. Let me find a fresh sheet of paper. Here we go. Okay, a stereoisomers, and there's enantiomers. And then there's similarly stereocenters or stereogenic centers, and more specifically chiral centers. So, chiral centers. Okay, so broadly, stereocenters are if you swap two groups, stereochem is changed. And now you've switched between isomers. Okay, so that's the definition of stereocenters. So examples of stereocenters. If you have a cis-trans bond, if I swapped out this hydrogen for this CH3 group, it would become the trans instead of the cis. Right? Do you agree? I don't know why I asked that like you guys could respond. You're at home. And you're probably not watching this anywhere close to when I'm recording it. But so this is cis and trans are interchanged by swapping these out. So this is a stereocenter as well as this. This could also be a stereocenter. Sometimes it's kind of referred to as in the middle of this bond here, but more simply, it's at that carbon where you can swap out two groups and interchange between isomers. Now, also, if you have a chiral center, this is also a stereocenter. Because if I swapped out two of these groups, it changes between the R and S notation. So I'll just go ahead and draw that for you. I'm pretending like I'm looking at it from between these two. This is where my little person is hanging out looking. I don't know. I just got my stick figures going crazy. They're looking at it right there. So from that angle, your chlorine's on this side, and your fluorine's on this side, and your bromine's here, and your CH3 is there. So CH3 is the lowest priority. It's already pointing away. Amazing. So let's see. This would be 1, 2, 3. So that one is S. And then here on this one, you have, again, I'm looking at it from right here. So this is where my little person is. There we go. I'm struggling today. Chlorine, and then bromine, and CH3. Oh, wait, no. I was drawing that one again. Fluorine here. CH3 on this side, if I'm looking at it from this direction, and then bromine is pointed away from me, and chlorine is pointed away from me. So in this case, it would be 1, 2, 3. and that's S, but the S lowest priority group is pointing towards me instead of away from me, so actually this is R. So swapping that out changes from the S stereoisomer to the R stereoisomer. So stereocenter is a broad category to refer to a center where if you interchange two groups, it will switch between stereoisomers. A specific type of stereoisomer is a chiral center. It is a type of stereoisomer, and it's this type specifically. That's all it is. I know maybe I shouldn't have even brought up the word stereocenter. I just kind of wanted y'all to be aware of it. But yeah, so you don't have to worry. You don't have to worry too much. This is a broad definition. It's kind of like how shampoo is a type of soap, but not all soap is shampoo. This is the shampoo. This is the soap. Chiral center is a shampoo. Stereocenter is the soap. A chiral center is a type of stereocenter. Stereocenter broadly encompasses, for this class's purposes, cis or trans, and that's it. There are other types of stereocenters that are more complex that can happen right in the middle of bonds like we talked about, but you don't need to know those right now. So that's it. That's all a stereoisomer is. So I just kind of wanted to touch base on that. Okay, let's come back to, the reason I wanted to touch base on that is so I could show you here, both of these could be considered as a stereocenter, right? They're not a chiral center because it's not a tetrahedral atom with 4 things attached to it, 4 different things, but it is 2 different types of isomers, 2 different types of stereoisomers. So if you interchange at either one of these carbons, that would be considered a change between 2 stereoisomers, specifically between 2 diastereomers. And so that would indicate that there's we're shifting from cis to trans. So we've already gone over cis and trans, but I'll show you. I like to draw my line. It's got 2 carbons instead of 2 hydrogens, but because these groups are the same, we can still say it's participating in cis-trans isomerism. So this is trans and this is cis isomerism. So that's trans, that's cis, and this is a stereocenter. Okay, now this one's a little difficult. I'll tell you that for me, it's easier for me to imagine wherever the lowest priority group is, I stand on the opposite side of that. So I imagine like I'm standing here. This is my little person. And they're looking directly at this molecule between the bromine and the chlorine. So from that angle, it looks like the bromine would be coming out on my right. The chlorine would be coming out on my left. And the CH3 would be pointed kind of back away from me, and so would the hydrogen be kind of pointed back away from me. So to draw it out, it'd be like this: HBr, Cl, CH3. And once you've drawn it into the Fisher projection, it's actually really easy. We just number 1, 2, 3 for high priority. This is 4, 1, 2, 3, so that is R. For this one, let's do the same thing. 1, 2, 3. This is S, but the hydrogen's pointing towards us, not away from us, so it's actually R. So I'd say these 2 are identical. They're not meso compounds. Okay. They're not meso because there's not 2 chiral centers with a plane of symmetry. They are just the same. It's just 2 different ways of drawing an R configuration of the same molecule. I did get that question a few times. Okay, now this one, this is basically the upside down version of this, so it's kind of hard to visualize. Oh my gosh, you guys, my husband brought me a cupcake. It was someone's retirement party. Look at this. It's so cute. It fell over. I don't care. It's so cute. There's this really cute bakery down the street from our house called Candy Haven, and they make these really good cupcakes with really good frosting. That's so sweet. He's so nice. Okay. Moving on. So this is basically the upside down version of this. So what I do, again, is I orient myself to where I'm looking at this molecule, because it's easier for me to imagine myself moving than to imagine the molecule moving. I imagine I'm floating on top of this molecule, looking down this way. So then the hydrogen would be pointed away from me. And if I was looking down that way, the CH3 would be over here. The CH2, CH2, CH3 would be over here, and the chlorine would be pointing down. So then I can just number that, 1, 2, 3. And I'm not going to go through the priorities because we've done that a few times, so that would be S. Now also, you can do it to where you swap your groups. Let's see if this works. CH2, CH2, CH3. I think if we swap this hydrogen out with, the way I drew it was like it's a Fisher projection, but it's not. I think if we swap this hydrogen out with that chlorine, we could put the hydrogen here and the chlorine here. That hydrogen's still coming towards us. See, I'm bad at this. This is why I do it the other way. Okay, CH3 is coming towards us. Chlorine is coming towards us. And now I'm going to make the hydrogen go away from me and the CH2, CH3 be down here. Oh, it's CH2, CH2, CH3. So this would be 1, 2, 3. So that would be R, but because we flipped it, we're in the looking glass. Through the looking glass, is that what you say? Because we're through the looking glass, it's actually S. So either one of these ways that you want to approach it is fine. So let's see. Which one did I pick first? I did this one first. So now we'll do this one. And again, employing my method of laying down on the ground, you could do that, or we could swap it. So the hydrogen's already pointed away from us, so we don't even have to swap it. Amazing. So let's just do 1, 2, 3, and that should be R. So this one's R and this one's S, so the answer here is enantiomers. Okay, so we have the relationship between these two are enantiomers. The relationship between these two is they're the same molecule. They're not isomers. They're identical. And it's not a meso compound because there's not two stereocenters. These are diastereomers. They're cis-trans diastereomers. And we talked about where the stereocenters are on that, although you're not responsible for that for the exam. And then up here, I believe we decided these were enantiomers and we found the RNS configuration. So again, if you can just visualize it, that's fine, but I like to do the RNS configuration. Okay, now let's go down here. This was the one that was causing you all the trouble. So there's no double bonds here that are capable of cis-trans isomerism. So we're not looking for anything. The only stereocenters that we will have here are chiral centers. And chiral centers are tetrahedral centers with 4 things attached. And sort of like this nitrogen, I could maybe see if there's 2 different things attached, how that might be a stereogenic center, but actually because this lone pair is there, it can interconvert between the R and S configuration. So typically, if the nitrogen has 4 different things attached, which in this case it doesn't because it goes all the way around the ring and these are identical, right? Then in that case, I could see it possibly being a stereogenic center, but it has to have 4 different things attached. And this only has 1, 2, 3 different things attached if you count the lone pair. So when I'm looking for stereogenic centers, typically what I do is I start around a ring. Rings are good ones for that, but this ring has alternating double bonds and they're all sp2 hybridized, so you can't have an sp2 hybridized stereocenter, right? So all those are the same. So there's not one there. Then I look here, but these 2 rings are exactly the same. So that's not a stereocenter. This might be, but it's a symmetrical ring. So these 2 things attached on either side are the same. All these points have 2 hydrogens. This has 2 hydrogens, 2 hydrogens, 2 hydrogens. This is promising. It has this long chain over here, this ring over here, an alcohol and a hydrogen. So I'm going to say yes. This right here, that's a chiral center, also known as a stereocenter. This sp2 hybridized all the way around. And then right here, these CH3 groups are the same, so that wouldn't be it. So there's only one stereocenter, chiral center in this case, specifically in this molecule. Now let's go down to this one. Okay, so again, this is sp2 hybridized all the way around this ring. So there's only one hydrogen around. So none of that can be. And then there's 2 hydrogens on that carbon right there. This ring is promising. Nope, 2 hydrogens here, 2 hydrogens here, 2 hydrogens here, 2 hydrogens here, and it's symmetrical around. So none of that is not this or this is. Now this right here, sorry, that doesn't have 2 hydrogens. I lied to you. I think this, oh, it's not symmetrical all the way around. Okay, pause. Ignore what I said. This one has more stereocenters. So this nitrogen does not have identical things attached to either side. So this nitrogen could be a stereocenter, although the lone pair does make that difficult. So I'll go ahead and star that nitrogen for now. This has 2 hydrogens. This has 2 hydrogens. So neither of those are anything. This nitrogen, again, has 2 different things attached to it. So I'll go ahead and star that nitrogen. And then this, this carbon right here has 2 hydrogens attached to it. But this carbon right here has a CH2, a nitrogen, and then this group and a hydrogen. What is this group called? An amide. So I see 3 chiral centers right here. 4 if we're counting this nitrogen here as well, because it has a hydrogen, this carbonyl group, and this CH3 here. So that's several different things. Okay, so rings are good places where you can find chiral centers. And then we're going to keep going down the chain. This one has 2 hydrogens, but this one does not. It has 1 hydrogen, and on one side a nitrogen, and or like a chain to a nitrogen, and on this other side a chain to an amide. So this is also different. So that one has 1 too. And then this looks promising as well. This has a hydrogen here, and then 2 CH2s. So that's similar until you get to the next one where this adds to a benzene ring, and this has an alcohol. So that's a chiral center. This has 2 hydrogens, and all these are sp2, so none of those will be. This is sp2 hybridized. This nitrogen, if we're counting nitrogens, could be one. And it has the dash notation actually to show you. And then let's see. This has 2 hydrogens. These are all sp2 hybridized, so none of those could have it. So right here, this has 1 hydrogen, but then an asymmetrical ring around it. So both of those are chiral centers. So I count up 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9 chiral centers on this one. Oh, okay, good. I was worried that I was out. That's not 12. That was me counting up. So 9 chiral centers on this one. Okay, sorry, my lighting on here is weird. Okay, so one thing I want to point out is I did count nitrogen in here, but because nitrogen has this lone pair, if there was 3 different things attached, actually this nitrogen interconverts rapidly between 2, even though it has 4 different things bonded to it technically, because it's a lone pair and then, carbon, nitrogen, whatever. It rapidly interconverts between the RNS configuration, because basically this lone pair can trade places with it too. The lone pair isn't stuck in one place. That's kind of a confusing thing. So if there is a test question on this, I will note whether or not you should consider nitrogens as chiral centers or not. Usually, the convention that I'm aware of is that if nitrogen has a positive charge and 4 things bonded to it, that's the only time you note the chirality, because otherwise, if it has 3 things and a lone pair, it can interconvert so fast that you don't usually note the chirality, because it's kind of impossible to isolate one or the other with that lone pair. So I would say this is kind of like a gray area on whether you should call it a chiral center or not. It does have 4 different things. It does have handedness, but this lone pair goes back and forth so rapidly that it's not always noted. So here I did note the nitrogens, but that was just to help you see areas where there are 4 different things attached. So you could practice seeing the 3 different things bonded to the nitrogen plus the lone pair. but I will specify, okay, you do or you don't need to include nitrogens. I'll say, how can I phrase this? Not, what's the word? They're not sp hybridized, neutral nitrogens with lone pairs. Okay. Draw each structure below along with its mirror image. Indicate whether the compound is chiral or achiral. Hint, look for a plane of symmetry. All right, so here we go. Cis12 Dimethylcyclopentane. So I'm going to start with a parent chain. Cyclopentane, this is really good practice for naming as well. So we have cis12 dimethyl. So I'm going to number it. Here's one methyl, here's the other. I made them both wedges because they're cis. Okay, so right away, I see a plane of symmetry right here in the middle. So even though these are both chiral centers, and the reason they're chiral centers is because there's a CH3, there's a hydrogen, there's this C carbon with a hydrogen off of it. This should be a dash over here. But over here is just carbon with 2 hydrogens. So this is the point of difference. So this is a chiral center. And so is this for the same reason. It's not the same chain all the way around. So there's 4 different things attached to each of these. But because of this plane of symmetry right here through the middle, this should be a meso compound. So this is achiral or not chiral. And just to double check, you can always build the structure and see, to help you visualize that the mirror image of this, it has 2 things poking up. So the mirror image also has 2 things poking up. So you should be able to just rotate it around and make them still both. I'm not good at making this shape with a ring. I'll do it like this. 2 things going up. The mirror image also has 2 things going up, so if I rotate it around, they would both, the same exact group, be pointing up. You'd have to pretend my pinkies and my thumbs are the same, but you get the idea. I should probably just pull out my modeling kit, but that sounds hard. Okay, so now we're going to do the same one, but we're going to do it with trans. And I have a sneaking suspicion this will be chiral. So both CH3s, these are again both chiral centers, but in this case, there's not a plane of symmetry right down the middle, because if you reflected this across itself, it would need to also be a wedge. One's pointing up and one's pointing down. So if you took the mirror image of one pointing down, one pointing up, and then you tried to rotate it and put it over top of each other, these 2 are pointing opposite and these 2 are pointing towards each other. So it has 2 chiral centers. And it is a chiral molecule because there's no plane of symmetry. Okay, and then this over here, let's see, CH3, C, Cl, Br, H. So I don't see a plane of symmetry here. I see a carbon with 1, 2, 3, 4 things attached to it. I only see 1 chiral center, so that must mean if it only has 1 chiral center, we don't even have to check for a plane of symmetry, because 1 chiral center means that its mirror image would be non-superimposable, so this is a chiral molecule, and there's no plane of symmetry. Okay, let's look at D. CH3 too. Oh, well, that's already a good sign that it will be a plane of symmetry. I'll try to draw these in the tetrahedral arrangement. CH3 2, we have a hydrogen coming out towards us and an alcohol. Okay, so if you drew, let me draw this a different way. I think it'll be easier for you to visualize. H, and then we have our CH3 coming out towards us here, and a CH3 coming out towards us here. If you drew a plane of symmetry right in the middle of the page where it would reflect this CH3 across itself, then you can see it's reflecting a CH3, so that would be correct. So this is achiral. It also doesn't have 4 different things attached to it. So if you just look here, it has 1, 2, 3, and then this is the same thing. So there's not 4 different things attached to it. So that tells me that it's achiral. Okay, now let's look at this one. And I knew it was CH3. I think some of you might be like, how'd you know it was CH3 like this and not like this? And that's because this is CH3CH2. But it said CH3 2 times in parentheses, so I figured they were both around that middle carbon. No, I was off camera that whole time. That's heartbreaking. Okay, well, hopefully you could follow what I said with that. How is that happening? Maybe I really should just make the plunge and get a new camera stand, I think. Okay, so the next one is CH3, CH2, CH3, CH2, CH with, there's an OH off of it. And then CH3. You guys should recognize this, hopefully. 1, 2, 3, 4. This is 2-butanol. We've done this a few times already. So 2-butanol, right here at this carbon, has CH3 on one side, CH2, CH3 on the other, OH over here, and a hydrogen. So this has 4 different things attached. So this is a chiral molecule, and it has an enantiomer. Sorry if you can hear rattling in the background. My husband is getting into some hot fries because he acts like a 12-year-old. Okay, he doesn't really. He's a grown-up. Okay, CH3, CH2, this is F, CH with an OH off of it, CH2, CH3. So the reason I went ahead and drew it out just because it was easier to follow, but there's an OH right here in the middle. So I'm going to say this is not a chiral molecule because there's these 2 here and here are exactly the same. So there's only 1, 2, 3 different things attached to it. So I think we decided this is achiral, and we decided this was chiral. Oh, wait, no. We decided, achiral, chiral, achiral, chiral, chiral, and achiral. Okay. Now the next one is write a procedure for assigning SNR in your own words. We did that in class today as a group already, so I'm not going to go over that. And then the next one is show the stereogenic center by labeling them with a star and determine the configuration of each R or S. Okay, so here, that middle one right here is the stereogenic center because there's 3 different things attached to it. And I'm going to go ahead, I'm going to imagine I'm a little person laying down here on the ground and looking up. So if I did that, my chlorine would be on the left, and my alcohol would be on the right, and my methyl group would be pointing straight down, and my hydrogen would be away from me because I'd be laying on the ground looking up. And so this is 1, 2, 3 priority, and so that is S configuration. Now here, we have 1 chiral center right there. It has CH2, CH2, so that would be the same, but here it has CH and CH2, so those are slightly different. Remember with carbon-carbon double bonds, it acts as if there's 2 carbons, so the first one would be CHH, CHH, those would be the same, here and here. And then when we get here and here, it's as if it's bonded to a carbon, and a hydrogen, and this one over here is carbon, hydrogen, hydrogen, so the one on the left wins. So that one's 2 and this one's 3, and then we have an implied hydrogen pointing away at us. So that implied hydrogen's pointing away at us, so that's going to the left, so that's S. Okay, and then now I do want to point out technically this is also a stereogenic center, each of these, because you can have, I guess it's not technically, if you had a substituent here and here, this would be cis, but if you had, so technically it's not, but if you had this and then this, that would be trans, right? So if you interchanged right here at the double bond from one side of the bond to the other, then you are changing the stereoisomer, so that would be a stereocenter. So in this case, because the double bond only has hydrogens around it, that's not, wait, I think what I just said was wrong. Yeah, what I just said was wrong. Ignore that. Ignore that. Don't pay attention to that. You can't change in between cis and trans because it's a ring. So ignore that. There's only one stereocenter here, right there on the bromine. Sorry. Probably just confused you worse. But again, I'm not going to ask you about stereogenic centers. I'm only going to ask you about chiral centers. Okay. Now in this one, the hydrogen's already pointing away from us, baller, so we just have to do 1, 2, 3, and that's going to the right, so that's R. And now in this one, here is your chiral center. These two are both CH2. This is hydrogen because it's 1, or this is alcohol, so it's 1. And then this hydrogen will be 4. These are both tied at CH2. So then we have to go down one more. Bromine is bigger than chlorine. So it'd be 1, 2, 3. So that's S, and the hydrogen's already pointing away. So S, S, R, and S. Okay, draw the following molecules in bond line formula. Oh, hang on. Okay, my package came, yay. Now I can go back into my normal room and not kneel next to my coffee table, which is uncomfortable. But I'll finish this video and then switch. Okay, so this says draw the following molecules in bond line form. Specify the stereochemistry using bold and dashed lines. So what I'm going to do first is draw out the molecules. So this is really good practice again for chapter 4. So this is butane. 1, 2, 3, 4. Where'd my other marker go? In the chaos of my package getting here, I lost it. Okay. This is butane. So 1, 2, 3, 4. I'm just going to number it. What's nice about when they give you the name is you don't have to worry about how to number it because they already tell you. So 1 bromo, 2, 3 bromo. Okay, so usually what I do actually is it needs to be S. So I always just make the hydrogen or whatever is the lowest priority point back. And then I figure out which one it is. So this is 1, this is 2, this CH3 is 3. So this is going to the right. So this is R. Well, it needs to be S. Hey, that's fine. I can make that happen because all I have to do is switch this to be a wedge and this to be a dash. And there you go. So this should be S dibromobutane. Now to make sure, I will calculate or find the stereocenter. I found my purple marker. Okay. So bromine is 1, CH2 is 2, and CH3 is 3. 1, 2, 3. So that's R, but my hydrogen's pointing away from me, so I'd flip it back to make it S. Or if you want to flip the whole molecule over this way, you could do that as well. The bromine would then be on that side. And your hydrogen, your bromine would then be coming towards you and your hydrogen would be coming away from you. And you could do 1, 2, 3, and then you could see the S. So whichever way works for you, just do that and do that consistently. So I always just start when I'm drawing these with the hydrogen pointing away, and then I figure out if it's R or S with the hydrogen pointing away, and then I just flip them. So the next one is 3-methylhexane. 1, 2, 3, 4, 5, 6. Hexane, 1, 2, 3-methylhexane. So again, I'm just going to make this the wedge and have this implied hydrogen here point back. So these two are both CH2. This one is CH3, and this is CH2 with a C. So I'm going to say this is the highest priority, and then this one, and then this one. So this is S, actually. So we're going to flip it to make it R. And you can double check my work if you want to. Or you can flip it over. Flip the molecule over, and then your CH3 is coming towards you. And your hydrogen's pointing away from you. 1, 2, 3. There we go. And that's R. So if that's S, then this is our right answer. So make sure if you're doing this like on a free response or question, you make sure you box the right one if you're using this method, because if you had both drawn and they weren't labeled R or S, that might be confusing. But I just wanted to show you guys how I always do it. So then the last one is S-butanol, 1, 2, OH, 1, 2, 3, 4, it's 2-butanol, and then the hydrogen's going back. This is 1, 2, and 3, so that is R, so then S is going to have the OH as a dash. There we go. Okay, so that's question 3, and then for question 4, this is the last one. Name the following molecules using IUPAC nomenclature with specification on the stereochemistry. Okay, so 1, 2, 3, 4, 5, 6. So this is hexane as the parent chain. And I'm going to highlight this parent chain. This is good practice for those of you who were struggling with nomenclature on quiz 2. If it's in the parent chain, you don't need to name it as a substituent. So this only has one substituent, this alcohol. So 2-OL. So this would be hexane 2-ol. And then we need to say if it's R or S configuration. So I'll use yet another pen color to do that. So this is 1, 2, 3. And then we have an implied hydrogen pointing towards us. So 1, 2, 3. That's R, but the hydrogen is pointing towards us. It should be pointing away from us, so this should be S. So we would call this S. Wait, did I do that? Yeah, you don't need to put the number if it's in there. S hexane 2-ol. If there was multiple stereocenters, you'd have to clarify. Okay, now this one, let's find the parent chain. Let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so we have a few different options for what the parent chain could be. When there's multiple options, you want to choose the one with less substituents. So if you go this way, we have 1, 2 substituents. And then if you go this way, or actually you do the one with more. If you go this way, 1, 2, 3, 4, 5, 6. This one has more substituents. You pick the one with more substituents because it's usually simpler to name. If you'd done it the other way, then you'd only have 2, but they'd be more complicated to name. Like this one is, if you have this group, if we'd gone this way, 1, 2, 3, 4, 5, 6, and then you had this group up here, this is isopropyl, right? But an IUPAC name, it would be 1-methyl-ethyl, 1-methyl-ethyl, or like 2-1-methyl-ethyl. So it's more complicated. So you want to choose the one that has more substituents if you have 2 options of parent chains that are the same length. So technically we could have done this parent chain. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. But because that would only give you 2 substituents, this isopropyl group and this methyl, that's the less good option. So we're going with a pink one. And then we have to decide how to number it. 1, 2, 3, 4, 5, 6, or I'll use this. 1, 2, 3, 4, 5, 6. Okay, and now let's identify our substituents so we can decide how to do that. 1-methyl, 1-ethyl. Okay, so there's either going to be 2,4-dimethyl and 3-ethyl, or there's going to be 3,5-dimethyl and 4-ethyl. So this one's better. So we'll start with the naming here. 1, 2, 3, 4, 5, 6. Okay, so now we have our name all put together. 2, 4. Oh, did I ever write out that the parent chain was hexane? I don't think I did. 2,4-dimethyl. Ethyl comes first. 3-ethyl. 2,4-dimethyl. There's no space between this, but I ran out of room. Hexane. So that's the name overall, but we have to name this, we have to specify the stereochemistry of the stereocenters present. And let me see how many stereocenters I find. This is the only one that has a wedge and dash, so I think that's the only one, but just in case, I'm getting a clean piece of paper. This has 3 hydrogens, 2 hydrogens. This clearly has several different things attached. Oh. I think this is also a chiral center that we missed when we made this. This has 2 hydrogens, 3 hydrogens, 3 hydrogens. This has 2 methyl groups. So all these are the same. This one right here has 2 different groups attached to it. So there's actually 2 chiral centers. Only one gives us the wedge or dash notation though. So am I crazy? 1 hydrogen, 1 CH3, 1 CH with big crazy groups over here, and then 1 CH2. No, I'm not. This is also a chiral center. That's what I thought. It doesn't give you the wedge and dash. I'll just assign a wedge to this CH3 to make it happen, so that we can decide to do that. But yes, so there's actually 2 chiral centers there. I was looking at that and thinking, I don't think that's right. So I'm glad I checked. Okay, so this right here, we have the hydrogen already pointing away from us, so that makes life easy. We just have to assign priorities. So this one is CHH. This one is CHC. Yeah, C, H, and C. And then this one right here is C, C, H. So actually, these two are the same priority, and this is the next lowest. So this would be 3. So now these two are still competing right here. They both are attached to a carbon. This is the same, CH3, so that doesn't weigh us one way or the other. But this carbon is CHH, and this carbon is CHC, or no, HHC. So this would be the highest, and then this one. Okay, so 1, 2, 3. That goes left. So that one's S. So at carbon 3, 3S. 3S. And then we also need to assign at spot 4. So I just arbitrarily assigned the hydrogen to be the dash and this CH3 to be the wedge. And then we have to assign priority. So this is the lowest priority. And then all these are carbons. This carbon's attached to 3 hydrogens. So that's going to be the next lowest priority. Actually, I'll do this one in a different color. 4 on the hydrogen, 3 on the CH3, and then again, these two are tied. They're both carbons, but this carbon is attached to 2 hydrogens and a carbon, and this carbon is attached to 2 carbons and a hydrogen. So this one wins. So this is 1 and 2. 1, 2, 3, we connect in order, and it's going to the right, so we'll call that R. Okay, so our full name is, I'm going to rewrite it, 3S, comma, 2R in parentheses, and then you do a dash, and then you do 3-ethyl 2,4-dimethylhexane is this full name. So I start by doing the parent chain, then I identify the stereocenters, and then I name it. Okay, let's come down here. There's only one stereocenter on this one. Let's find the parent chain. Parent chain is right here. There's not a lot of branching it can do, so that one's pretty straightforward. 1, 2, 3, 4, 5, 6. So this is again hexane. Wow, you got a lot of hexanes going on here. Okay, hexane, and then at position 3, you have 3-iodo, 3-methyl. So I would say iodo comes before M, so 3-iodo, 3-methyl hexane, and then we have to say whether it's R or S configuration. So this is CH3, that's going to be the lowest, well, this is the highest priority. And then these are all carbons, but this carbon is attached to 3 hydrogens, so that's the next lowest. And then these two are both CH2, so you keep going down the line. This is CH3, and this is CH2. So it has a carbon and 2 hydrogens, and this has 3 hydrogens. So this would be 2 and 3. So we connect 1, 2, 3, and it's going to the left. So that would be 3S, 3-iodo, 2-methylhexane. Now this one, we can do one of two things. We can just say these are both wedges, so we can actually just say cis. Alcohol is the higher priority, so we'll start there. Cis2 chlorocyclo. There's not a space there, but I ran out of room. Hexan 1-all. I actually don't know if you have to put the 1 there. So you can just say cis, that they're both wedges or they're both dashes. Or if you want to be more specific, I would accept either one. You can label the R and S configuration. So if we were to do that on this one, there's a hydrogen pointing backwards, so we don't even have to worry about that. And then 2, 3, 1, 2, 3. So 1 is R because it's going to the right. And then on this one, this is 1, 2, 3. The hydrogen is pointing back, so this is 2S. So yeah, I would name this 1R, 2S, 2 chlorocyclohexanol. And if you're ever not sure, 1R, 2S, 2 chlorocyclohexanol. And if you're ever not sure about cyclohexanol, you don't have to put a 1. I think the only case is if it's an alcohol that's substituted on it, because you assume it's the 1. That's annoying to me. So if you're ever not sure, if you put the 1, I won't count off. Okay, and now the very last activity, this is a Newman projection. So we're doing the Newman projection and then identifying the stereochemical details. So what I'm going to do is I'm going to draw this front carbon first, and I'm going to actually draw it just as it appears, even though it's not in your classic bond line formula. So we have an H going up, and then if I was looking at it, so this is it flat. So we have our H pointed up, and then if we turn it this way, and I'm looking at it from this angle, which is typically how we do it, your CH3, I'm going to do my H going straight up. What? Oh, sorry. Your H is going straight up. It's in the plane of the page. Sorry. And then you have a CH3 dash that's going into the plane of the page. And then over here, this would be a wedge, right? So CH2, CH2, OH. And then you have a straight line back to carbon 2. So I'll do carbon 2 in a different color. Now your thing that's coming straight down is your CH3. And then coming out at you, because if this is flat and you rotate it, like say my finger is the thing going straight down and I rotate it, it's going to still stay flat in the plane of the page. The hydrogen becomes a dash, and the CH2, CH3 becomes a wedge. Okay, so now before I do anything, I'm going to stop, and I'm going to make sure that I drew this right. So I'm going to use this bond line formula, and I'm going to make sure that I can recreate the Newman projection. So if I'm looking at it from this angle here, I have a hydrogen that's in the plane of the page. I have a CH3 here, and I have a CH2, CH2OH. And then if I have the back, sorry, I keep going off camera because I'm not on my normal desk. Okay, so then for my back carbon, I have my CH2, CH3 here, CH3 going straight down, and a hydrogen on the left. And that is the same Newman projection, so I feel great about that. Now you can do one of two things. I like to imagine that I'm laying on the ground here and looking up. And if I was doing that, my CH3 would be on the left, and my CH2, CH2OH would be on the right, and then this whole group would be going straight down. And then my hydrogen would be pointing back away from me. So if that's the case, let's see, what's the highest priority? These are all 3 carbons. This carbon has 3 hydrogens, so that's priority 3. And then between these two, these are both carbons. This carbon is attached to 2 hydrogens and a carbon. This one is attached to 1 hydrogen. Okay, so this is 2, 1, 2, 3. So I find that to be S configuration. You can also swap out 2 and find it that way. I'm fine with that. And then now for this one, my hydrogen's already pointing back. Praise, we don't have to do anything. So this is 3. These are both C8. Well, these are both C's. This is CH2. So this is bonded to 1 carbon, 2 hydrogens. This is bonded to 2 carbons and 1 hydrogen. So this is 1 and this is 2. So then I get that one to be R. So I would name this. Oh, now I have to do the whole parent chain, don't I? So it has to include the alcohol. So 1, 2, 3, 4, 5, 6. Just to make sure, I'll go over here. 1, 2, 3, 4, 5, 6. Yep. Okay, so this is hexane. Again, wow, lots of hexane. But on the first carbon, there's a 1 OL, right? And then 1, 2, 3. 3 has a methyl. And the reason I know that this is where we start for numbering is because alcohol is the highest priority. And then it looks like 4 also has a methyl. And then 5, 6. So my final name on that would be 3,4 dimethyl hexane 1-all. And then I would make sure that I have 3S4R 3,4-dimethyl hexane 1-all. That would be my full name. Okay, hopefully this was helpful to you. I know this is kind of a lot. There's a lot of practice here for you to do. I hope that you have time to go over it before the exam because all this could come up on your exam. Okay, happy study.